Hi guys, this is Mrs. Foy, and this is a screencast on hearing, taste, and smell. I'm making these screencasts for my own class, which is a introduction to human anatomy and physiology. So this is meant to be just a very brief introduction to these senses. I actually also have a video on just the eye. So I have a YouTube video on just the eye. I'll try to put the link right below where you're looking. And the other thing is that if you would like to have access to this presentation, just contact me, leave me a note here on the YouTube page that you're on right now, and I will be happy to share that with you. So guys, today I'm going to talk a little bit about the senses of hearing, taste, and smell. And one of the crazy things that we see when we look at these different receptors is that they all have the same signal. They all have the same signal that they are sending to the brain. So let me erase my scribbles that I put here before. So for example, you have receptors in your skin that react to touch and pressure or pain and temperature. And all of those receptors send the same signal to the central nervous system, and that signal is something called an action potential, which is just a wave of electricity where that has to do with the ions flowing in and out. You have receptors in your nose and on your tongue that respond to certain chemicals. When they fire, they send an electrical signal, this action potential wave of electricity, to the central nervous system as well. You have receptors in your ear that respond to sound waves, and they respond by sending this electrical signal of action potentials to the central nervous system. You have receptors in your eye that respond to light, and they are going to send these wave of action potentials to the central nervous system. And we also have special receptors in our ear that have to do with equilibrium and our body's position in space, and they send action potentials or electric impulses to the brain as well. So what's my point? My point is that all of these signals are the same. All of these signals are the same electrical signal that is sent from these receptors. What interprets that is the brain. So depending on where these signals go, our brain interprets those electrical signals as sight or sound or something that we're smelling, like our grandma's chocolate chip cookies, something like that. So let's take a better look now at what these receptors actually are. So let's take a look at those. So there are different types of receptors, and this is a list of the different categories. So for example, we have these receptors called rods and cones that are examples of photoreceptors. And photoreceptors react to light. And so the cones actually react to colored light, and rods respond with black and white. But those are the special type of receptors that respond to light. They produce action potentials that are sent to the brain. We have mechanoreceptors in our ears, and these mechanoreceptors, you see this word mechano, they don't react to light, they react to being physically deformed or moved. There's these little hairs that we're going to see up here, that when these hairs are bent, that triggers electricity or an action potential, a flow of ions to be produced in these mechanoreceptors, which are sent to the brain. We have chemoreceptors. These chemoreceptors are smell, if they're in our nasal membranes, and taste, which are in our taste buds, which are on our tongue. These react to specific chemicals. They don't react to mechanical deformation. They don't react to light. They react to chemicals. And what's their reaction? They produce an action potential, a wave of electricity that is sent to the brain to be interpreted. And finally, we have other mechanoreceptors in our skin that are similar to the ones in our ear, except this time when we mechanically deform these, they send a signal to the brain that interprets it as touch or pain or being pressure, having pressure, deep pressure, light pressure. So at this point, if you're in my class, I'd like you to stop what you're doing and watch this app called Visible Body on Vision, just to review a little bit of vision. You can also watch the video that I made about the eye. So let's first of all talk about mechanoreceptors in the skin. Remember that your skin is an organ. The skin is an organ because it's made of many different types of tissue. And in that tissue, we have different types of receptors that are responding to different things. We have bare nerve endings that are usually responsible for pain. We have things called Meissner's corpuscles and Merkel discs that respond to light pressure and deep pressure, and some of these actually respond to vibrations. You can see all these different here, Pacinian corpuscles and Ruffini endings. These all, we're not going to go into the specific detail in this class, but these are all different mechanoreceptors, and when they are stimulated, with the special thing that produces an action potential in it, be it pressure or light touch, they're going to produce an action potential that's going to go through a bundle of nerves to the central nervous system, and the central nervous system is going to interpret that as, hey, somebody just pushed on my finger. So if you're in my class, again, I'm going to ask you to stop. Oh, no, sorry, that's the next slide. Sorry. Let's take a look now at the mechanoreceptors in the ear. So these are a little bit different. So the mechanoreceptors in the ear actually have these little tiny hair cells that stick up from them, and it's those hair cells that are actually mechanically deformed. So as we're going to see in just a minute, there is fluid in the ear that can move back and forth, and depending on which way the fluid moves, it's going to mechanically move these little hairs, and that creates a signal. Right? That creates a signal that then goes to the brain, and our brain interprets this either as a sound or, in some cases, as we'll see, as the position of our head. And we're not going to go into a lot of detail about this, but this is just the pattern of the action potentials here, and you can see that you can either stimulate, you can produce more of these signals that go to the brain, or you can actually inhibit that produces less of these signals. And this hyperpolarization just means that the signal is harder to produce. All right, so let's take a look at the actual anatomy of the ear here. So guys, we have three parts of the ear. We have the outer ear. We have the outer ear that basically is everything that you see and where you could put a Q-tip. Although my daughter, who is a speech therapist, tells me you should never put anything bigger than your elbow in your ear, but I know a lot of people like to use Q-tips. We also have our middle ear, and our middle ear is going to be this area right here. Every place from your eardrum or your tympanic membrane in. And then finally we have our inner ear, and our inner ear has these crazy looking things in here, these specific organs that are responsible for sound and also our equilibrium. We also have a tube that is used, it's called the eustachian tube, and this particular tube helps to equalize pressure. And so sometimes, and this actually drains into your pharynx. And so what happens is that sometimes if you get an infection there, sometimes those microbes can get up into your middle ear and vice versa. And sometimes that's how we get ear infections. So let's take a look at what we're going to be doing here. Now, let me just generally say that what is happening in the outer ear is that the outer ear is kind of like a big funnel, right? It's going to direct sound waves into our ear, and it helps to kind of amplify those. So these sound waves are going to be amplified and moved into this area right here, which is our eardrum. Our eardrum is called the tympanic membrane. When it starts to vibrate from these waves hitting it, it's going to cause these three little bones to vibrate, and then that passes the signal on to another little window that we have here that has fluid on the inside. So this is where the fluid part of our ear is. So our ear is going to be basically responsible for two main functions. One is hearing, And so the organ that is responsible for that is called the cochlea. So it looks like a little snail, and then you can see this is the cochlear nerve. This is going to be a bundle of all those axons that we're going to see from those receptors that are going back to the brain, and the brain is going to interpret these things as sound. We also have another part of our brain, of our ear, that has to do with what we call static equilibrium. The saccula and the utricle have to do with when we are still, and this affects our balance and our sense of where we are in space. Even with our eyes closed, we can tell. So this has to do with our static equilibrium. And then these lovely things that are all at right angles to each other are called the semicircular canals. And these have to do with our dynamic equilibrium. So understanding where our body is and our head is when our body is in motion. So we're going to explain those things now. So the first thing we're going to talk about is the cochlea. So we're going to talk about the cochlea, and the cochlea is just for sound, right? So this is an organ that is just going to be for sound. And the saccula and the utricle are going to be for static equilibrium. And then the dynamic equilibrium is the semicircular canals, right? So the ear has a lot of different things in it. I bet you didn't know that. So basically, guys, this is what is going to be happening in our ear. And this specifically is the cochlea. So we can see that this is now in our inner ear, right? So this is in our inner ear. And there is fluid that we're going to see. There is fluid that is filling this ear. So what is going to happen is we have these mechanoreceptors. They have these little hairs, and then there is a membrane that kind of floats on the top of this chamber, kind of like a roof. And what happens is as fluid goes through these tubes, it's kind of coiled up like a little snail. What happens is it causes this roof of this membrane to move back and forth and vibrate and causes these hairs to bend. And that is the thing that sets up an electrical signal that is then sent through these nerve bundles that go to the brain. So what is happening here is, again, we have a sound wave that is amplified in the outer ear, and then it hits our eardrum. And in our eardrum, when those sound waves hit, it starts to vibrate, just like the head of a drum. That's why it's called the eardrum. It's going to start to vibrate. And what starts to happen is that these three tiny bones start to vibrate. It's almost like a chain reaction. So one starts to vibrate, the next starts to vibrate, the next starts to vibrate. And what happens is that it is going to hit the, there's a little area here called the oval window that is the entrance to the inner ear, which is fluid filled. And so here is our cochlea. Remember, it looks like a little snail, and the fluid starts to vibrate in there, and that's what's going to actually cause those hair cells to be depressed. So here's the whole thing. So we have sound coming in. It's going to hit our membrane, our tympanic membrane. This causes the three little tiny ear bones in your inner ear to start to vibrate. I'm sorry, the middle ear. This is our middle ear. And this is the malleus, the incus, and the stapes. And they're going to start to vibrate. So this starts to vibrate. This guy vibrates. He passes the vibration on to the next guy, passes the vibration onto this next guy. And then there is a little window right here. And this window is the entrance to the fluid-filled chamber of the cochlea. And what happens is that there's going to be a wave of fluid that results from this sound wave that started all this vibration, and that is going to cause those little hair cells to bend, and that sends up the action potential. What's really cool about this is that there are different frequencies of waves that are going to be responsive at different parts of the cochlea. So we have high frequency waves. These are going to be high sounds, medium frequency waves, and low frequency waves. And we can see that we have special places on our cochlea that are going to respond to this frequency of wave. So at this point, actually, let me go back for just a second. Let me talk just a little bit about hearing loss. One of the things that we recognize is that when you are exposed to very high levels of sound, what can actually happen is that the little receptors, the hearing receptors, can actually become paralyzed and not function anymore. And so if that happens, like listening to your earbuds really loudly, or having a loud engine or a machine that's running beside you, it actually causes these not to function. And so in a particular part of your cochlea, you may have certain sound waves, frequency of sound waves that you cannot hear. So I love my father-in-law. He has passed away, but I always used to tease him because he was hard of hearing. He was a veteran, and it was hard of hearing. And he could never hear my voice, but he could always hear his son's voice, my husband's voice. And I always used to tease him and say that maybe he didn't want to hear me, or he just wanted to hear his son. But obviously he had hearing loss in the certain frequency that affected my range of voice, and not his son's. Although maybe he did really want to listen to him anyway. So guys, if you're in my class at this point, I'd like you to stop and watch this Visible Body video. By the way, a great plug for this app called Visible Body. It is amazing. All right, guys, so let's talk now about static equilibrium. So what is happening here is this is in the saccula and the utricle, and what is happening here is the same kind of thing. So we have fluid, and you don't need to know in my class the name of all these things, but you have these little hair cells here, and we also have these tiny little, almost kind of little tiny stone-like structures called otoliths. And what's happening is as the fluid is moving back and forth, these little otoliths are going to be depressing these hair cells in different positions depending on how you're holding your head. And that causes certain of these mechanoreceptors in the utricle and the saccula to fire and produce an action potential. And those action potentials, that wave of electricity goes to your central nervous system, goes to your brain, and your brain can interpret where your head is compared to the rest of your body, even with your eyes closed. I know I've moved my head left, I've moved my head forward, and that is because of this action of these mechanoreceptors in specific areas of those two structures. So again, if you're in my class, you might want to stop and watch this Visible Body app for just a second on static equilibrium. Now guys, we can also tell where our head is and our body is when our body is in motion. So this would be an example of, like, if you're riding a roller coaster. You would still know where your head and body is in reference to each other because of the semicircular canals. So what is happening is, again, same kind of MO. We have a fluid-filled chamber, and we have these little hair cells that are here. And what is happening is that as your head rotates, the fluid is going to move in a wave over, and what happens is that these little hair cells are depressed because they are mechanoreceptors, and it sets up an action potential that is then sent to the brain, and the brain interprets that is our position of our head and our body when we are in motion. So guys, olfaction. Olfaction is smell. And these are a different class of receptors now. These are chemoreceptors. And so these chemoreceptors respond to, you guessed it, different chemicals. And so these different chemicals have specific shapes, and they fit into the receptor of specific chemoreceptors, just like a puzzle piece. And so these are actually located on this top part of our nasal cavity here. And notice that it is very, very close to the deepest part of our brain, which we're going to talk about in just a second. So what happens is that these receptors are going to be responsive to chemical shapes. So they're not responsive to light, like the eye. They're not responsive to pressure or touch, like our mechanoreceptors. They're actually responsive to certain chemicals. And when those specific chemicals hit, they find specific receptors that are going to mesh with that particular shape, and that causes the cell to produce an action potential electrical signal that is then sent up to, gosh, guys, I have this backwards. Here is the axon right here. I apologize. So what is happening here, so sorry, what is happening here is that we have the receptors here. So sorry. And so then their axon is going to be sent up this way, and the receptor is going to go send that information to the brain, and our brain interprets that as smell. So we have some really interesting theories and what we've learned about what odorant is just going to be a molecule that is going to fit into one of these receptors. And it turns out that some of these odorant molecules fit in different types of receptors. And the different combination of these different receptors is what gives us the smell that we are going to interpret, our brain will interpret as sweet or sour or smelling like a rose or something like that. Now, what's really cool about this is that these olfactory receptors are very, very close to the limbic system of the brain. And the limbic system of the brain is where we have our emotion. And so of all of the senses that we have, smell is the one that is the most closely related to our emotions. And so that is why when you go to your grandmother's house or you smell a certain perfume or cologne, it might elicit a certain emotion. And so that's why that is, and I just think it's very interesting. Olfaction is one of our most ancient evolutionary senses. So this would be a good time to watch that video on olfaction. All right, guys, our last sense today is the sense of taste, which is also a chemoreceptor. And so if you stick out your tongue and take a look at your tongue, you've got these little bump things on your tongue. Those are called papillae, and embedded in those papillae, we have our taste buds. And so our taste buds are going to be embedded in here. And so what's going to happen is it's going to be a chemoreceptor, and these certain molecules are going to fit on here, this time though in our mouth, not so much what we smell. And then it's going to set up, if they fit in that lock and key, it's going to set up an action potential or electrical signal that is going to be going to the brain, and our brain will interpret that as a taste. Now, what's interesting, of course, is we know that taste and smell are very closely related. If you have a cold, food is not going to taste as well. And so our brain interprets both smell and taste very closely together. We're still trying to figure out how taste buds work. We used to think that there were certain areas of your tongue that had receptors for a certain type of taste. So we had, for example, I think sweet was on the front, supposedly. And we now know that that is not true. But we do have these 5 different classes of taste receptors. We have bitter, we have salty, we have sweet. Umami is the Japanese word for savory, so something like tasting a nice hamburger or something like that. And then we also have sour. So we know that certain parts of our tongue do not have certain regions that for these 5 different categories of taste, but we're not exactly sure how it works. We don't know if we have these different categories like this with our taste buds, or like this, or some combination like that. So we're not really sure how they work, but we do know that that is what sets up the action potentials that go to our brain, that our brain interprets as taste. This is a great video about super tasters, and I put the short URL here if you're interested in watching that. It's really funny. Some people are super tasters and some people are not, or sub tasters, and there's a funny thing you can do with blue food coloring to find out what you are. And then, of course, my hero is Bozeman Biology. Dan Anderson has some awesome videos. If you have not seen those yet, this one particular one on the senses is a 10-minute video that's going to go into a little bit more detail than what I did, but I hope you'll find it helpful. So I hope that that was helpful, and I will see you in class.